Okay, in this chapter, calculus students, we're going to learn about concavity, which is the curvature of a function. And the second derivative test is another way to find maximums and minimums and extrema in a function. Now, what is concavity? Now, you actually had an introduction to this way back in Algebra 1 when we first started talking about parabolas, like y equals x squared. This was a happy parabola. We call it happy because it had a positive, it looks like the smile's going up like that. This is concave up. And something like y equals negative x squared is concave down. Concave down. But it doesn't have to have the shape of a parabola to be concave up or concave down. Everywhere along the parabola we consider this to be concave up. This is concave up and increasing. This is concave up and decreasing. Here's concave down and increasing, and then concave down and decreasing. Here's a more formal definition now. F is going to be concave up when the graph of F lies above all of its tangent lines. See these tangent lines in blue? And the graph is always above it. Some people like to think of the concavity as like a bear in a cave. Here, this is the cave. This is the cave. This is the outside. And so the cave is above the curve. So we consider that concave up. Cave. Here, formal definition is when the graphs of all the tangent lines stay above the curve, then the curve itself is concave downward. And notice in these situations, as you go from left to right, the slope is changing. The slope is increasing when it's concave up, and therefore the derivative is increasing. And when it's concave down, the derivative is decreasing. Now let's see how this plays out then when we actually look at a function. Here's a function, 1/3 x cubed minus x. And before, we could set the derivative equal to 0 to find out where we have our max and mins. These are critical values. Here's the derivative. I'm going to put it right underneath the function. And notice at x equals 1, the derivative is 0. At x equals negative 1, the derivative is 0. And sure enough, that's where we have a relative min and a relative max. But what happens here at 0, negative 1? Well, notice that this original function is definitely sad over here on the left. So this is concave down. And notice how the derivative is decreasing. And here on the right, to the right of negative 1, it's happy. And the derivative is increasing. So right here where you have this change in concavity, that thing right there is called an inflection point. And we'll study more on that later. Now, Theorem 5.7 is coming up. It's a parallel of Theorem 5.5. It's how we use the second derivative to determine the type of concavity. Notice how we use the first derivative before the first derivative being greater than 0. Told you that f was increasing. And if the first derivative was less than 0, then f of x was decreasing. Now, we see that if the second derivative is greater than 0, then the original function is concave up. And if the second derivative is less than 0, then the original function is concave down. Third case is what if it happens to be equal to 0, and that's where we're going to look for inflection points, or if it stays constantly 0, then it's linear. If you're neither concave up nor concave down, you're not curved at all, and it's a straight line. Okay? So example 1, determine the open intervals in which the graph of this function is concave up or concave down. Well, let's find its first derivative, and we might find it handy to think of this as 6 times x squared plus 3 to the negative 1. Just to do the derivative easier, the first derivative then is negative 6 x squared plus 3 to the negative 2 times the derivative of the function, which is 2x. And so we have the first derivative is negative 12x times x squared plus 3 to the negative 2. Now this is where the second derivative would probably be kind of handy for this, to do it on the calculator. But let's just practice doing it up by hand here. I'm going to shift to the quotient rule and write this as negative 12x over x squared plus 3 squared. So by the quotient rule now, to do the second derivative now, quotient rule, bottom, x squared plus 3 squared times the derivative of the top, which is negative 12, minus the top, which is negative 12x, times the derivative of the bottom, which is going to be twice x squared plus 3 times 2x all over the bottom squared. Oh, this is getting messy. So, for the second derivative, we've got x squared plus 3 is a common factor on the top, so let's take that out, and also the 12 as well. Let's take out a negative 12 times x squared plus 3 out of the top. That's going to help a lot, because then we are just left with one x squared plus 3 left over from this group here. From this group, we took out the minus 12, so it's going to be minus 2x times 2 is 4x, minus 4x squared. So that makes x squared minus 4x squared plus 3. So that becomes negative 12 times x squared, negative 12 times negative 3x squared plus 3 over x squared plus 3 cubed. So now let's factor out the negative 3, and so we get the second derivative. Take the negative 3 out of these two, and we get 36 times x squared minus 1 over x squared plus 3 cubed. So the second derivative will equal undefined, never, because there's no way to make division by 0, because it's x squared plus 3. The second derivative will equal 0 when the top equals 0, so when x squared minus 1 equals 0. And that gives us our two numbers, plus or minus 1, to consider. And so let's look at those in a chart. We want to look at negative 1 and 1. And I want to try some points on either side of those as well. So here's x's, here's the second derivative, and we're going to see what that implies about the original function f of x. Well, negative 1 and 1 make the second derivative equal to 0. We're going to see what that creates. So let's try some points in between. When we try 0 into the second derivative, you're going to get 0 minus 1, so negative 1, negative 36 over something positive, so that's negative. So that means in the middle we're going to be concave down. You can use CD to represent concave down. If we put in 2 up here, 2 squared minus 4, that's going to be 3. That's going to all be positive. So that means we're concave up on the original function. And if you try negative 2, the same thing happens, because negative 2, all that gets squared, so you get 4 minus 1 is 3. So that's positive, so that means the original function is concave up as well there. So we see this changing in concavity. We're concave up for the intervals negative infinity up to negative 1, or from 1 out to infinity. So these are the concave up sections. But in the middle, it's concave down. Concave down for the interval from negative 1 to 1. And so what happens right here? Where it's changing concavity, we call those inflection points. Inflection points. Or IP for inflection point. Okay. Now here, example 2. Determine the open intervals on which the graph of f(x) equals x squared plus 1 over x squared minus 4 is concave upward or concave downward. Now, it's a lot of work to go through these derivatives, so I'm okay if you want to just use your calculator to come up with the derivative. Let's try that. Let's put this on our calculator. Okay, to find the second derivative on your TI-89, here's the command, the little d symbol, which is above the 8, left parentheses, now put in the function, so left parentheses x raised to the 2 plus 1, right parentheses, divided by left parentheses x raised to the 2 minus 4, right parentheses, comma, x, you're taking the derivative with respect to x, comma 2. This is how you can quickly jump to the second derivative. And the calculator tells me 10 times 3x squared plus 4 all over x squared minus 4 all raised to the third. Okay? So how can we use this now to determine when it's concave up and concave down? We can look at when is the second derivative equal to 0 or undefined. Well, it's equal to 0 when the numerator, 10 times 3x squared plus 4 equals 0. This is never. Never, because you're starting off with 3x squared plus 4. You set that equals 0, you're going to get imaginary answers. So we're going to have better luck figuring out when it's undefined, and that's when the denominator equals 0. So that's when x squared minus 4 equals 0, or when x squared equals 4, so x equals plus or minus 2. So we end up with those two things as candidates for when it's defined or undefined. And so now I'm just going to add another little chart here. And look at what happens at -2 and what happens at 2. So these are like critical numbers, but we formally define critical numbers as things that made the first derivative equal to 0 undefined. Now these are like candidates for possible inflection points. So here we go. Here's x. Here's the second derivative. We determined that -2 and 2 make it undefined. Undefined. So let's see what this does in terms of creating about the original function, f. So let's try some points on either side of these candidates. So recall, here's our second derivative from the other page. And I want to try some points in between here. 0 should be easy enough to try. You put 0 into here, and the bottom's actually negative. The top is positive, so the whole thing's negative. So it's concave down in between -2 and 2. And let's try a point like -3. -3, that's all going to be positive, and on the bottom, that's going to be positive. So it's going to be concave up there. +3, same thing. The whole second derivative is going to be positive, so that's going to be concave up there. Concave up. So, sure enough on the graph, we find that between -2 and 2, it's concave down. And as we go beyond 2, or to the left of -2, it's concave up. Okay? So those are the intervals. Concave upward, let's sum that up. On the intervals from -infinity up to -2, or from 2 to infinity. And it's concave down on the interval from -2 to 2. Now notice in this case, we did not get an inflection point, because the function doesn't exist there and you've got a vertical asymptote. And that's our next topic, these points of inflection. And we've talked about this for a long time. It's when you change concavity. But also you have to have an actual defined point there with a tangent line. And so we consider this an inflection point as well. Some books don't, but we're going to consider this an inflection point. Even though it's a vertical tangent line, it is still a function, and so we call that an inflection point. In fact, that comes up in our definition. If the graph f has a tangent line at the point c, f of c, then this point is the point of inflection if the concavity f changes from upward to downward or downward to upward at this point. So note the definition above requires the tangent line exists. And this is what I was talking about. Some books don't actually let this happen. In this case, here we have a change of inflection on this graph, but because you don't have a tangent line that exists at that point, because the directional derivatives don't agree. Here the first derivative is 3x squared, or it's 2x plus 2. If you approach 0 from one side, you get a slope of 0. If you approach from the other side, you get a slope of 2. So because you don't have a set tangent, fixed tangent line there, it is not an inflection point. So, if you've got a point of inflection on the graph, then either the second derivative is 0 or it does not exist at x equals c. So let's investigate this. Determine the points of inflection for this graph. Now this derivative is easy enough to do by hand. 4x cubed minus 12x squared. And let's do it again for the second derivative. 12x squared minus 24. 0, because it certainly can't be undefined. There's no division by x here. So 12x times x minus 2 equals 0. So we get x equals 0 and x equals 2 as our possible inflection points. But we have to check to make sure there's a change in concavity. It's not enough that the second derivative is 0. You've got to make sure that you have a change in concavity here. So I'm going to investigate x equaling 0 and 2. Those both make the second derivative equal to 0. And so that's why we're checking these out. Let's see what happens with f of x. So let's try some points. Between 0 and 1, 2 is 1. When we put 1 into the derivative, we're going to get 12 minus 24. That's negative 12. So that means we got concave down on the original function. Let's try 3. 3 in here will give us something positive. So that means it's going to be concave up. If we try negative 1, we're getting negative 12 times negative. That's positive. So again, concave up. So since we see the change in concavity, we know we have an inflection point here and a change in concavity from concave down to concave up, so we have an inflection point here. So that means, what are the actual values here? When you put 0 into the original function, you get 0. So this is the point 0, 0. And when you put 2 into the original function, you get 4 times 2, 32 minus 12 times 48. And you get this negative 16, which is what shows up over, no, not quite negative 16. Let's try that again. When you put 2, I say I put in the derivative. 16 minus 32 is negative 16. Oh yeah, that looks about right. There's your inflection point at 2, negative 16. And here's another inflection point at 0, 0. Okay. The converse is not generally true. That is, it is possible for the second derivative 0 to point if there's not an inflection point. For instance, the graph of this. See, because we're not having a change in concavity here. You look at the first derivative of x to the fourth, you get 4x cubed. You look at the second derivative, and you get 12x squared. The second derivative is definitely 0 at x equals 0. But the second derivative stays positive on either side of that candidate. So therefore it stays concave up on either side, so you don't have an inflection point. So that's why it's important to check. Now this is a nice exploration, and we can talk about that more in class, about how every cubic has an inflection point. What I want to get into now is the other main application of the second derivative, and that is the second derivative test. And you notice here we have an example of a minimum and a maximum. And when it's a minimum, we usually find these extrema by saying the first derivative equal to 0. And certainly have that in this case, where the slope is 0. So if you've got the first derivative equal to 0, and you know it's concave up, it must be doing a minimum. If it's concave down with a 0 slope, then it must be a maximum. So the second derivative test is tricky here. You look at your possible candidates for a relative extrema by saying the derivative equal to 0. The second derivative exists, and if the second derivative exists then, if the second derivative is greater than 0, then you've got a relative minimum. Now some people think that this is backwards. No, this is quite forward, because the second derivative being greater than 0 implies that it's concave up. If you're concave up, you're like this shape, and so you must be looking at a minimum. If the second derivative is less than 0, that means you're concave down. If you're concave down, you have this shape, and that's why it's hitting a maximum. If the second derivative is 0, you can't use this test. It fails. Or if the second derivative or the first derivative is undefined, notice you don't have a second derivative. So this second derivative test has its limitations, but in some ways it's considered more efficient because in the first derivative test, remember, you had to go on either side of the critical numbers to see if you actually went from increasing to decreasing or decreasing to increasing. Now, just taking the second derivative of the same critical number can tell you what's going on. So find the relative extrema of this using the second derivative test. So the first derivative is negative 15x to the fourth plus 15x squared. And so first we can find the critical numbers. That's by setting the derivative equal to 0. So in this case, I'm going to factor the negative 15x squared out, leaving behind an x squared minus 1. Set that equal to 0. That's our first derivative. And so we get x squared equals 0 or x squared equals 1. So we get x equals 0 or x equals 1 or x equals negative 1. We've got three critical numbers. Now before, what we'd do is we'd look at all the points in between each of these numbers to see if the derivative is changing sign or not. You don't have to do that with a second derivative test. Got another little trick here we can use. We can say, okay, the second derivative is negative 60x cubed plus 30x. Or if we take the derivative test, is you'd leave spaces between all your critical numbers because you'd want to test what the first derivative was doing in between all these. We know the first derivative equals 0 at each of these, and so then we would usually set up space on either side of this to see what was going on with the first derivative, to see if it's increasing and decreasing or whatever. But with a second derivative test, you don't have to do that. With the second derivative test, you just look at the second derivative of your critical numbers. If you put negative 1 in here, we're going to get something that's positive times positive is positive. So that means it's concave up. The original function f is concave up there. So again, here's our different critical numbers. And negative 1, 0, and 1 all make the first derivative equal to 0. But they make the second derivative equal to different things. They put negative 1 to the second derivative, I get a positive quantity. That means the original function is going to be concave up. And if it's concave up, that means you have a relative min. Where does that occur? When you put negative 1 for x into the original function up here, you get negative 3, or positive 3, minus 5 is negative 2. Negative 1, negative 2. Here, when we put 0 into the second derivative, you get 0, so there's no conclusion there. The test fails because the second derivative has to be either positive or negative. If it's 0, you can't tell it's a relative max or min. Here, when we put positive 1 in, as opposed to negative 1, we get negative 30 times something positive, so that's negative, so that means it's concave down for the original function, and you have a relative max. At 1 comma, put 1 into the original function, you get 2. A relative max at 1, 2. So sure enough, there's our relative max at 1, 2. Relative min at negative 1, negative 2. And here at 0, 0, it's got a 0 slope. But it doesn't have, it goes from increasing to increasing again, so it's not a relative max or a relative min. Now, just to review the first derivative test for comparison, I'm going to do the first derivative test in red so you can see the difference between these two tests. In some ways, I like the second derivative test more because you don't have to do as much messing around. If I had the second to do the first derivative test on this, I'd have to call up the first derivative again, which is over here. And we have to try points in between all these, like negative 2 and negative 1/2 and 1/2 and 2. and see what's happening to the sign of the derivative. Well, here's our first derivative. Maybe a better form of that first derivative would be 15x squared, let's say negative 15x squared times x squared minus 1. And when you put negative 2 in, you're going to end up with negative. So that means the original function's decreasing. When you put negative a half in, that's positive. That's negative times negative, that's positive. So the original function's increasing. And sure enough, if you go from decreasing to increasing, you have a relative min. If you put a half in, we get negative times negative, that's positive. So this is what I was talking about. You go from increasing to increasing over this critical number, so there's no max or min. Finally, when you put 2 in, you get negative times positive is negative, so that means the original function is decreasing. If you go from increasing to decreasing, it's concave down, it's a relative max. So that's just a little review of the first derivative test. The second derivative test, I think you see, was a lot less calculating. Okay, flange out.